See, a lot of people didn't make it because of the rain, I guess. Hello? That was sort of to say it's time to quiet down. All right. So last time we introduced the notion of when you have more than one particle. I only use two, but there's a sort of straightforward way to extend it to more than two particles. And I didn't assign any homework. It's actually just in the homework. But there's a way to write down combinations of particle 1, 2, and 3 minus particles 1, 3, and 2 plus particle 3, 2, 1 minus particle, you swap the things around. Anyway, there's a prescription for symmetrizing and anti-symmetrizing multiple particle systems. Symmetrizing or anti-symmetrizing the wave functions, right? Such that particles are indistinguishable. Physically, we say that in quantum mechanics, and mathematically, because I do this sort of shell game where I put the shells down, and at the same time I switch the shells and put them down again. And I say the real state is a combination of the shells one way and switched the other way, so that that mathematically I can't ask a question which distinguishes different particles. And then I talked to you about the fact that the symmetric and anti-symmetric combinations, which I just introduced mathematically, I put a minus sign when I added the two states or not, actually has a physical meaning because the anti-symmetric states, and I didn't really prove it, but I showed you the example in the book where they'd worked it out. The anti-symmetric states tend to be spatially different, whereas the symmetric states tend to be spatially the same. And the extreme is that if the state is the same, then the symmetric state is clearly the same particle, the two particles in the same state. And if the two states are the same, the anti-symmetric state is absent. It's just mathematically zero. That is the statement of the Pauli exclusion principle, which you may well have heard, which is that two particles that can't be in the same, that have to be anti-symmetric, can't be in the same state. And we said, well, spins, it turns out, are the key to this. Yeah?
Is the opposite true? Like if you have two bosons, they have to be in the same state?
They don't have to be in the same state. No, right. Because this was, psi, state 1 of particle 1, psi, state 2 of particle 2, plus psi, state 2 of particle 1, psi, state 1 of particle 2. That was a perfectly good symmetric wave function. And it involved state 1 and state 2. It's just that for this, I could have, I can do that. But if I had the negative sign there, it vanishes. All right, so bosons can either be in a symmetric, bosons can't be in an anti-symmetric state. Let's be very clear here. I think I mentioned that we're kind of entering into the part of quantum mechanics where the math is straightforward, but the ideas are coming thick and furious, okay? A boson, an integer spin particle, has to be in a state of this form, a symmetric state, but that's a distinct idea from whether or not it's in the two particles are in the same individual states. They can be or not be in the same individual states. Now I said spin, we said spin was completely related. How do I combine this idea with spin? Well, first off, I hadn't really shown you this, but, oh no, I did show you this. The way I'll talk about spin is I'll say that is a spin up. For an electron, that would imply ms equals plus one half, for the example of an electron, or spin down, which is ms equals minus 1/2, okay? That's an arrow pointing down. All right. So what I can do is, for instance, I really have to consider everything. When I wrote 1 here, where the book likes to write n and n prime, this n is a shorthand for all of the things about the state. The L, the R, the M, etc. So for instance, I could write spatial state 1 of particle 1, spatial state, it could be 1 of particle 2. Let me construct an anti-symmetric state that's valid. Minus spatial state 1 of particle 1, spatial state 1 of particle 2, This looks like it's going to vanish, but if I have spin included, let me say that particle 1, and I'll just use the convention that the first thing I write is particle 1 and the second thing I write is particle 2. In fact, I really should just start doing that so I don't have to write of x1 here every time and of x2. This can be like that, and this can be like that, the other way around. And that's a perfectly valid state. Okay? Because you see that I can just factoring terms, that's psi 1 of x1, psi 1 of x2 times what looks more like we just did last time, an antisymmetric state in the spins alone. You see that? I just did algebra, a tiny bit of algebra there. All right? So that's writing it down mathematically. You should write that down. It's straightforward, but it's just a tiny bit subtle. Make sure you understand that. Make sure I did get it right. Yeah. And in words, I'm just saying, look, you have to consider the spin also. The state, and this is an important concept, the state may be in a spatially symmetric state. The electrons, two electrons could be in a spatially symmetric state as long as these spins are antisymmetric. And there was no antisymmetric state that had both spins up or both spins down. That just vanished because you'd subtract it and it would go to 0. All right? Or I could put two electrons in the same, and this is key. I put this on an exam last year and a bunch of people missed it. Now I got your attention, okay? If I put two electrons, can two electrons be in the same spin state? Absolutely. If the spins are combining along, say, with different L. Let's just consider two electrons that have different L, and they have their spins, and I make an overall wave function. If the two particle states are different, and I antisymmetrize that, then they can both go spin up or both go spin down. That's fine. It's just that the overall thing has to be antisymmetric. They can even be in an antisymmetric, a boson can be in an antisymmetric spatial and antisymmetric spin state, and that is overall symmetric. Right? Suppose I did this. Well, let me leave that one alone. But this new state here. This one, well, no. I run out of board space to do it. I could antisymmetrize this and keep that antisymmetric. And then if I swap them, I'll get a negative sign here and a negative sign there. And the overall sign will be positive. And that's fine for a boson. Okay? Is that clear? I don't want to write it down. Okay? So, all right. Now I'm going to write down something simple again, but it comes up a lot in atomic systems. And it kind of ties together the two things we've been working on to this point. So let's just go through it. Consider two electrons. And this happens a lot in real atoms. It's, for instance, something to think about in a helium atom that has two electrons. Or it happens in molecules. If I consider H2, the hydrogen molecule, the two electrons, to a large extent, they're going into a combined state. And so then we would think about it for that. Even though it is different because it came from two separate atoms with different orbitals, but similar concepts apply. I could think about creating an antisymmetric state of the spins. So that's an antisymmetric spin state, right? But remember, I also talked about combining angular momentum. So just kind of a different concept, right? I said, okay, so I should have a total S, which should be S1 plus S2, right? And then I said, well, graphically, I can write that down, and sort of graphically, it's some total S that came from S1 and S2. But then there was this notion that once I've done that, I get an S value, little s, not capital S. Sorry, yes, little s, not capital S. Let me write a T there. Okay, for total, which can be S1 minus S2 up to S1 plus S2, which in this case is equal to 0 or 1. Right? So remember I had all those notions. So in other words, these things, that would be, this is drawn would be the S total equals 1 state. The value of angular momentum, capital ST, is the square root of S times S plus 1, and this is just a reminder, would be root 2 H bar, et cetera. Okay? Let's combine these two ideas. I want to combine these two ideas, and I'm not going to rigorously talk about this. I'm just going to tell you how you combine these two ideas. Okay? Because these two, to be clear, the two ideas are that I should have thought about spins this way, where I add the numbers or subtract the numbers, the spin numbers, to get the total spin number. And then I have, for this, I have only m sub s equals 0, because there is no s. And here I have m sub s equals either 1, 0, or minus 1, corresponding to the component on the z-axis. All right? So that was one idea. The other idea was, boy, I ought to have these wave functions which are combinations like that. Okay? The two ideas combine nicely. That's a nice symmetric state for the electrons. And again, the electrons can be in that state if the spatial part is antisymmetric. So what do you think that would be in terms of the ST? If the two electrons are both up. I said that that's doing this. I'm aligning them. So this is ST of 1, and it's m sub s of 1. I could also have sort of aligned the two little s vectors, but done all of it downwards relative to some z-axis. That's this. That's ST of 1 and m sub s of minus 1. All right? Because, right, I did say m sub s is just, once I have an total angular momentum vector, it has different components along z. If s is equal to 1, if st is equal to 1, the values it takes on are 1, 0, and minus 1. The 0 turns out, and there's not a simple explanation for this that I'm going to go into in this class. It takes on this form. This is st of 1, ms equals 0. It's up, down, plus down, up. Okay? And the st equals 0, so therefore m sub s equals 0 state, which is antisymmetric, is up, down, minus down, up. Okay? This is in the book. You guys are seeming really blank. I mean, you happy with this? I'm just combining the two ideas. Before I started talking about symmetry and antisymmetry, I hope you knew this, right? Just how you combine two angular momenta. And then this is the way it maps onto this idea of making symmetric and antisymmetric states. The real surprise is this state here, where I've got up and down. I mean, the thing that always bothers me about it is I think, well, if it's up and down, how did that actually amount to the two guys, the two spins aligning to give the total S of 1? And sort of at some level, your classical expectation just sort of fails you. And there's a more general formalism that derives this, but we're not going to do that in this class. So I say this as a result. And I think less surprisingly, this state is ST of 0. This is called the triplet state because there's 3 of them. And this is called the singlet state. And these occur in many, many atomic systems. If you've done any chemistry, you may well have encountered singlets and triplets. And it's just that the two spins align to give you a total angular momentum of 1, in which case there were the 3 different values of the z component, the m sub s, or not. Okay? Just to give you one interesting example. Oh, sorry. And then what can happen is these states, if you have two electrons and they're going to form these states, suppose we're talking about a helium atom and you just talk about the spins alone. If I have two helium atoms, two electrons in a helium atom, if they form this state, the spins are antisymmetric, which has to be the case for the overall wave function. And in that case, like I talked about over there on the far left, the spatial states can be the same. So I can have two electrons in the lowest energy, the lowest hydrogenic potential, a hydrogenic orbital, and the spins are antisymmetric and you're fine. That's the ground state of a helium atom. That's what it just sits at. I can get and have this sort of behavior, but then I'm going to have to antisymmetrize the spatial parts. Okay? And since the ground state of an atom is n equals 1, L equals 0, there's no way to play with L. I simply have to pop one electron up to the n equals 2 level, and then I have to antisymmetrize the n equals 1, n equals 2 state spatially by doing 2, 1, minus 1, 2. And then I can have symmetric spin states. And so this is a higher energy state in a helium atom than this. And you can get transitions between an atom excited to this level or an atom excited to this level, etc. And I wanted to tell you one more just kind of far out thing. You guys just seem dead, but I'm going to do it anyway. This sort of thinking, one reason why I've labored a lot on this sort of thinking, because I don't know if I sense right, but you may be wondering why go on and on about things like this. This is sort of the fundamental way we start to think about all the topics that come next in quantum mechanics. Because lots of the behavior in quantum mechanics is dominated by these spins and by these rules about symmetry and antisymmetry, and symmetries in general. In fact, so much so that I've talked a little bit about the various particles of particle physics. And I've just mentioned that there's these things called quarks. You've probably heard of this anyway. There's a proton is 3 quarks, so is a neutron. There's 2 quark systems, the so-called mesons. They're very short-lived. If you create one in an accelerator, or there are many, many, many being created in this room every second, probably thousands by cosmic rays coming through and blowing apart nuclei. And they'll create these short-lived mesons. There's 1,000 particles in this room is nothing, right? But there are them. So this is a 2 quark system. If you look at the basic quark, the basic mesons, the lowest energy one is called a pion. Okay, it's a pi meson. I have the particle data book here, which is this handy-dandy book you can get from LBL, and particle physicists carry it around. And you can look up, once if you forget, okay, what's the mass of a meson? And I look up, and the pi meson has a mass of 139 MeV, about an eighth of a proton mass. It is 2 quarks in the singlet state, okay? And I can read right here, it says J equals 0. They call it J instead of S. It's in the J equals 0 state. And if I skip the page, there's a quark that's in the J equals 1 state. And it's got a mass about 5 times higher, 770 MeV. And the concepts I just told you to 0th order explain why the masses were different. It was because if I have 2 quarks and I combine them where their spins are anti-aligned this way, or anti-symmetrized this way, they can be in the same spatial state. If I want to put them with their spins symmetrized, I've got to put them in different spatial states, which is a higher energy configuration. And as I emphasized in the relativity part of the class, if it's a composite, if it's a thing where these little particles are running around, and I look at it from the outside, their kinetic energy amounts to mass. And so that higher spatial energy is giving it more mass. So I just explained a fact in here in a very hand-wavy way from the stuff I just told you. And I'm not BSing. These things come from these concepts, okay? So sorts of these rules about spins and stuff, a little bit dry it may seem, but the reason that we go through this is the way the subatomic world, this rules the subatomic world actually, these sorts of rules, okay? So I'll stop there. All right, so the last thing I want to do with quantum mechanics Yeah, and I do want to finish up today, and then we're going to quit in quantum mechanics. Is just to talk a little bit about the periodic table in chemistry. And I know probably you all have seen some amount of this in high school or here in college. And it may be a little bit of a refresher. But I think it's just worth going through, given what we've done here, and sort of, giving my take on building up the rules that lead to the periodic table. Okay. Okay, so the first idea is we solve the hydrogen atom for, we solved the hydrogen atom. And specifically then what I mean by that, I had one proton and one electron. And of course, if you have any other atom like carbon that we're made out of, or something exotic, francium, some heavy element, right? There's a lot of electrons. So first off, how can I apply what we did to those heavy atoms? Well, okay, that's what we're going to have to think through. One thing that happens is, what were the energy levels? The energy levels were minus 13.6 eV times 1 over n squared. And then n was getting bigger. And then what was remarkable about that is L didn't matter. Okay? It entered into the equation. There was the orbital term in the Schrodinger's equation, which I showed through magic, or appendix G, was exactly these theta and phi derivatives amounted to the angular momentum squared. But nonetheless, there was a cancellation, and in fact, the energy didn't depend on L. Okay, but that was due to the completely spherically symmetric Coulomb potential. And in a real atom, the influence of the various electrons on each other destroys that symmetry. So this goes away when it's no longer completely symmetric. I'm not going to write that down, but that's the basic concept. And so the actual energies do depend on L. So when I have multi-electrons, the energy is still something 1 over n squared, but also L matters. And I'm not going to write down a formula. N matters mostly, L matters next. So for instance, so basically if I make a chart and I'm going to plot energy going up, if I have n equals 0 at the bottom, that's also the only value of L that's allowed. I'm sorry, n equals 0, that's nothing. N equals 1, L is equal to 0. There's an energy there, okay? Next, I would jump up, and I would have n equals 2. And I'm going to have an L equals 0 state and an L equals 1 state. And actually, their energies really plotting the energy. In fact, let me put my energy axis right next to the figure here. Leave the labels outside of it. Sorry if you're copying that down. This is a slightly tidier way of doing it. Then I would have n equals 3, which has L equals 0, L equals 1, L equals 2. These states are actually kind of close compared to that difference. Just some more things, right? This was called the s orbital. Once again, L equals 0 is s, L equals 1 is p, L equals 0 is s, L equals 1 is p, L equals 2 is d. This is the spectroscopic notation, which was invented to describe the spectra seen from transitions of electrons between these states before anyone had any idea what was going on. Another thing I could say is, what is the number of electrons? We've done this before, but I think it's worth reviewing. There could be, sorry, not number of electrons. The number, well, it is I just want to be more precise. It's the number of states in which I can put electrons. There may or may not be electrons in there, depending on the situation. So I can put 2 electrons here because I can go, of course, spin up and spin down. This is one state. I can't anti-symmetrize the states, but I can anti-symmetrize the electrons. This is the same. P is L equals 1, so it has M sub L equals 1, 0, and minus 1. Those are all different from the point of view of the symmetrization stuff. So I get to include them as different, plus the 2 spin states. So that's 1, 0, minus 1, and then times 2 is 6. For 2, I get 2, 1, 0, minus 1, minus 2. That's 5 times 2 is 10. I just swallowed chalk dust. Okay? This is the number of states. If I add n and l, and this is not very fundamental, you don't have to copy this down, but let's just do it. N plus l is 1 here, it's 2, it's 3, it's 3, 4, 5. I think it's simple enough just to say you write down the n equals 1, you write down the n equals 2 and do its l's, etc. But this is another way of looking at the energy levels. People will say that the energy is proportional to n plus l. Except if you have the same n plus l value, and you can see that's happening, n wins, okay? So that's kind of a view of a lot of what's going on here. A few comments on it. Each of these is called a shell. There's a reason it's called a shell. It's because the radius, the average radius, basically goes like that. This is the expectation value of the radius of a state n in an atom with z. Goes like n squared, okay? So when I go from here to here to here, I'm talking about bigger and bigger and bigger radii, all right? Now, in a hand-wavy way, why does L matter? The reason L matters in a hand-wavy way is the L equals 0 state after n equals 1. This is kind of hand-wavy, but it's quasi-reasonable. It's also described in the book. The L equals 0, the S state, is spherically symmetric. The L equals 1 and higher L states are the ones that have lobes and whatnot. So for a high n value, the S state is going to be something like a shell or a donut, okay? And it's going to avoid the origin, whereas the L state will be lobes, say a 4-fold lobe pattern, that tends to sample the origin a little bit. That means it's sampling the deep part of the potential. If you go back to where in the previous chapter there were the solutions were plotted for the hydrogenic potential, the higher L states will tend to sample a little deeper in, which is a more negative potential, which is, and this is subtle, it also brings with it a higher kinetic energy. If you go to a lower potential energy, you sort of balance the magnitude of the potential and the kinetic. And so, something that's in close has got more kinetic energy, okay? And so that's this difference, why the asymmetric, when you go to higher values of L, it's higher angular momentum in a classical sense, and in a quantum sense, it's these more complicated orbital shapes. And then those shapes just have a higher energy, okay? And so that is pretty much, that's a lot of what underlies the periodic table right there. Okay. Is this going to turn on? No. Let's see if it will. Should I just cycle the power? Why don't we switch back and forth? Why don't you want to cycle the system and just see what happens? I can do this. I'll cycle the system. It's powering off. Oh no. No, it isn't. See, I'll stand right in front of the camera. Let me try to do in graphically what I was going to show you from a document from the book. While we fix that. Okay, no wait. I'll skip a step. This is a little bit out of order of what I wanted to say. Do what? Okay. There's another concept that we need in figuring out how the atoms behave. Yeah. If you're in an atom and you're an electron in one of these states, let's say specifically you're an electron in this state, and the atom and the states below you are full. So sorry, let me back up a second and say, what do I mean by that? If we take an atom like carbon, it has 6 electrons. Since these are the energies, what states are the electrons in? We can think of having no electrons on the carbon. You put the first electron on, it's going to go into this state. 2 electrons can go into it. They're always going to go in the lowest energy states first. And then it fills up. The point that I was going to come to is if you're an electron in this state, what do you see? Because of this behavior, this state of n equals 2, well, the first thing you might think, first thing you think is, okay, it's 4 times further out. And that's not quite right, though. It's 4 times further out, and there are these 2 electrons in this inner state. They were both actually in this nice spherically symmetric s orbital, the same state, and the spins were different. And so those 2 electrons basically screen the nucleus. All right? You might remember a result from electromagnetism. I don't know if you got this in your freshman electromagnetism, but that any spherical distribution of charge has the exact same Coulomb force law as a point charge. Is that familiar to you? Did you learn that? Works the same for gravity, right? That if we were sitting here right now and somehow some evil genie turned the Earth into a black hole that would be way down at the center of the Earth, we would feel the exact same gravity, right? Except that when we start falling, because it's not smaller than us now, but it's not higher gravity, right? Or better yet, if the sun turned into a black hole tomorrow, what would happen on Sunday? We'd just start getting cold. Nothing would happen to the orbit of the Earth, right? Because it's still, just because it's smaller, the gravity doesn't change. We wouldn't spiral into it. We wouldn't get captured. Okay. So that concept says that if I have electrons, it's really the same concept if you think about it. If I have electrons with a spherical symmetry, with a nucleus in the center, then those electrons just will screen Z. So these guys are out further. The inner ones will take 2 off of the Z, which will decrease R, but then N is bigger, which increases R. And so you sort of have these shells. It's, again, this idea of the shells. Each one is screening the last. And so all of these, by the time you add all 8 and you've filled the L equals 1 value with different values of m sub L, they will tend to, if you go look at those orbitals, they all complement each other in such a way that they fill in spherically, and then these all together are going to have 2, 4, 10 electrons screening the Z that the next electrons see, et cetera. And so that's how the shells get filled. All right? And so the atom doesn't just get arbitrarily large. In fact, that's another concept that you may not have ever thought about. Is a lead atom bigger than a hydrogen atom? You think?
Yes.
It probably, okay, why?
Well, we learned in chemistry, like, it's bigger as you go down and to the left.
So you know more chemistry than me. That answer is fine, but it has nothing to do with Z equals 82. I mean, that was the basic point I was going to make, is that there are differences as you go around the periodic table, but overall atoms are all about the same size, right? Density variations in materials are due a little bit to variations in the spacing of atoms, but they're more due to the nucleus mass changing, okay? And that's because as you go out, so Z is 82, N is 6 for the outer shell electrons in lead. So this is a factor of 36, but then you're dividing by 82. And the two things kind of compensate for each other. Not exactly, as you're pointing out, but they do. All right. So, yikes. So, where'd the ruler go? Oh well, I'll just point. So this graph I think is important. Over on the over here, you see exactly what I sketched on the board behind us, okay? That fundamentally, these concepts hold. However, when you're talking about electrons that are just going into the outermost shell at a time, things get more complicated, okay? And so while eventually, if I look at the 3 state, the S, P, and D, eventually they'll be ordered this way. When this shell is well below the energy of the 4 shell, initially though, after I filled 3s and 3p with 2 electrons here and 6 electrons here, there's just more complicated effects. The fact that this is not a true hydrogenic potential, the fact that this assemblage of electrons presents a non-spherically symmetric situation for the next electron that's going to go on, makes these energies cross, and the 3d is up here, and the 4s is the next electron, the next lowest energy. These get filled, then the 3d, and then once they're filled, this drops down below. This mixing point here, actually, what happens then is you don't get pure states that had an N and an L and an M sub L. And remember I talked about this notion of good quantum numbers. And the basic idea here is kind of related, is that you may not have a state that's really based on these N and L ideas purely, but the actual state that the electron's in is a mixture of things. And so it won't have a pure quantum number based on N and, with one N and one L. And then there's these hybrid states that are like that. Okay? So then if I take all of that into account, we get the periodic table. No. Okay, there we go. Which I'm sure everyone is familiar with, right? So We're filling in the S state. The first S state are written here and here. Then we fill in the 2S state that I drew here. Then next is the 2P state. As I move down this way, I'm going in the different ends, the different shells. Okay? When I get to this point and I fill the S and the P states, something sort of magic happens in that that's a very spherically symmetric, compact object. And the electrons are fairly tightly bound. And putting the next electron in is indeed taking the jump from one end up to the next one. Okay? And so then these are specially bound atoms called the noble atoms, noble elements. If I strip one electron out, this is a situation where these atoms would really like to gain an electron. If I add an extra electron, it's sitting there in a very exposed state, not very bound, and these electrons are easily stripped off. So these and these are very reactive elements. These two combine to form ionic compounds, etc. Okay. All right, so the extension of solving the Schrodinger's equation for a hydrogen atom does lead basically to the concepts which underlie all of chemistry, right? And sort of this is part of what I promised at the beginning of class, which was that when we are embarking upon talking about modern physics, we were going to be doing sort of obscure things. Quantum mechanics is, well, obscure is maybe not the right word, but certainly not what people thought, certainly unusual in many, many aspects. But it explains the most mundane, if you will, aspects of everything around us, all matter and all life, right? I've pretty much said everything I wanted to say, except I realized I've overlooked one thing in my notes, and it's just sort of a slightly ad hoc thing to add at this point. I don't know, it's just me, but I feel like I haven't treated you right unless I explain to you the notion of orthogonality of these states. Okay, so this will be your nice little nugget for the end of Friday. It's a simple concept. Oh, I can do it here. It's a simple concept. If, and it actually underlies a lot of what we've done, but I didn't really ever say it. And I'm not sure to what extent it's really brought out in the book, but I think you should know it. When we had, for instance, the particle in the box, the first state, or the state sub n was this, sine n pi over Lx. Okay? If I take psi 1, and I can star it, and psi 2, now star it doesn't do anything when it's just the sign, and I integrate over x, it turns out the answer over, in this case, 0 to L, depends on the condition. In general, it will be 0 to infinity, so let me just write that. Well, no, here it's 0 to L, just to be concrete. You can do this integral. And you're going to have to use trig identities because I'm combining the sign of one value of n with the sign of another value of n. The answer is that it's actually, in fact, let me do it a little differently. I shouldn't have put 1 and 2. I should put of n and m, i.e. this was, sine n pi L x, and that was sine m pi over Lx. The answer is that this is equal to 1 if n equals m, and 0 if n not equals to m. Okay? That's sometimes written as, this is sometimes written as delta n comma m. That's called an orthogonality condition. It's basically pointing out something that's kind of obvious if I draw it, which is that, for instance, the n equals 1 state looks like this, while the n equals 2 state looked like that. And then it goes along with this notion I tried to build of the symmetric states For two particles, it's different. That was two particles. Here I'm just talking about one. But it's the same in the sense that for the symmetric versus antisymmetric, I said the symmetric, the particles tend to be in the same place. Antisymmetric, the particles tend to be in different place. Just considering individual states alone, states of different values of n tend to be in different places. Right? When I squared these to get the probability, this one's peaked in the middle and this one's not peaked in the middle. It's peaked there and there. And the way it plays out, there's the thing that plays out mathematically, which is if I have this state multiplied by that state and I integrate, okay, it's 0. And the physical thing I want to get across is that that's a general result. In fact, and it's not obvious from what we've done so far, but it is a general result. And it's the sort of thing you'll spend your time proving in a more advanced class for quantum mechanics. It actually falls out of essentially linear algebra, when you take a linear algebra class, is that all solutions to with certain assumptions, all solutions to the Schrodinger's equation have that behavior. You get states with quantum numbers, and if I take two states with different quantum numbers, integrating them like that gives 0. Also, just spatially, they're going to be disparate. It even goes so far as and this was the reason this construction, the reason why I should star that. The reason I use this construction is because this is where I took expectation values, right? Okay? And so this is not, what is this asking? This is asking sort of how much did this state overlap that state? How much did this state overlap that state? They do overlap, but in a way, and you can see why this would cancel, right? If I multiply these two, what reinforces here exactly cancels here, and when I average it, it goes to 0. And it's a general result. You also have the fact that, for instance, a spin state up, taking the expectation value with a spin state up is 1. A spin state down, taking the expectation value with a spin state down is 1. But a spin state up, taking the expectation value with a spin state down is 0. Even though there's no integral here, and there's no physical meaning spatially to the spin up and spin down. They were somehow just this intrinsic properties. But I invent these little rules, and I follow the logic of them, and that's sort of something you do in quantum mechanics. So, I don't know why you guys are laughing at that. But it's true. Just to summarize again for today, and we're closing out. I mean, I talked about the periodic table and all that. And I talked about the fact that you're going to have symmetric and antisymmetric states for fermions and bosons. And I can either symmetrize the spatial part or the spin part. And then I finally closed off with this orthogonality notion that states that are different, and this also plays into what I was telling you about the different spatial locations of orbitals in an atom. States that have different quantum numbers spatially are mathematically designed so that when you average them, the product of them averages to 0, which is a statement that they're, as much as possible, given that I'm going to stick a particle into the box, the different values of n are finding states which are sort of spatially as different as possible. And this is a more precise way of stating that. And it also has all sorts of nice mathematical properties, which if you take a class in linear algebra, you will explore. Okay, and we'll stop there.